All right, a differential equation exam. Woohoo! And not just any differential equation exam, the third exam. Laplace transforms, series solutions, good times. 6 problems in our future. It's going to be a lot of fun. And of course, as always, let's start by putting our name, because after all, we won't get credit if we don't put our name. Okay, let's begin. Number 1. We're asked to find a few things, parts A and B. Let's start with part A. Find the Laplace transform 6e to the 2t cosh 3t. Now you might say, well, what is cosh? Well, it helps us. Cosh is e to the bt plus e to the minus bt over 2. There's a couple ways to think about the cosh function. One way to think about cosh function, it is the even part of the exponential function. And so in other words, if you were to split the exponential into an even part and an odd part, this is the even. Another way to think about cosh is it's kind of like the cosine function, and hence the name. See how there's a cosine there? It's also called hyperbolic cosine. All right, so what can we do? Well, we can use our definition here. Say, look, this is really the same thing as 6e to the 2t times e to the 3t plus e to the minus 3t over 2. And that's really the same as the Laplace transform of, well, 6 divided by 2 is 3. And then you can multiply the e to the 2t through, and you have e to the 5t, e to the minus t. All right, great. Well, now we just do them individually, right? And don't forget the 3. So I can put the 3 out front because the 3 is a constant. And what happens is that the Laplace transform, it's linear, which means that constants can come out. It's also linear, which means that we can break at addition. So the Laplace transform of e to the 5t is 1 over s minus 5. And the Laplace transform of e to the minus t is 1 over s minus a minus 1. So it becomes 1 over s plus 1. And that's it. We're done. We found it. Woohoo! Nice. Now we could put them together and get another answer, but that's perfectly fine. We just needed an answer, and here we are. Now you might wonder, is there a rule for taking the Laplace transform of cosh like there is for cosine? Yes! Surprisingly similar. Is it on our formula sheet? No! Because, we had to make choices. And because the cosh is really just involves pieces of exponential, we said, look, we'll put that one to the side. All right. But here we are, part A done. Part B. Consider the following initial value problem. So we have t x double prime of t plus 3t squared x of t is equal to the integral 0 to t of tau sine tau d tau with some initial conditions. X of 0 equals 0, x prime of 0 equals 0. All right. Now, what's going on? Well, it says if x of s is the Laplace transform of x of t, then fill in the boxes below. So we have boxes below for how this differential equation for x of t transforms into a differential equation for x of s. All right. Well, our work is cut out for us. Okay, so no worries. We can do this. We have really 3 pieces, and these 3 pieces here, so let's go through and talk about them one by one. So we'll start with the first term because why not? We should start at the very beginning. It's a very good place to start. So Laplace transform of t, x double prime of t. Now we should think of this as layers, right? A lot of these problems, when we talk about Laplace transform, is there's layers involved. And how do we get through the layers? Now you might say, well, what layers are you talking about, Steve? Well, there's really sort of 2 things. There's the x double prime is one layer, and then there's the multiplying by t is the second layer. So what we could say is, all right, first off, do we know how to take the Laplace transform of x double prime? Yes, it's on our sheet. Do we know what multiplying by t does? Yes, there's a rule. So we could say that multiplying by t says to do the following. It takes minus the derivative of what you would do if you just took Laplace transform of x double prime. So that's the t layer. Say, okay, well that's minus the derivative of, now Laplace transform of x double prime would be s squared capital X minus s little x of 0 minus x prime of 0. Well, we're in luck. These are both 0. So, gone. So, we have to take the derivative of s squared times x. And don't forget the minus sign. So, all right, product rule, two things multiplying. So, we have a minus. Derivative of the first would be 2s, capital X, and a minus the first times the derivative of the second, x prime. Okay, so those will be pieces. Now, we're not going to fill this in yet because we have other terms. Those other terms might interact. And so we'll wait before we put stuff into our boxes. All right, so on to the next term. Okay, so now we have Laplace transform of 3t squared x of t. Well, the 3 comes out. I say, okay, t squared. Do we know how to handle that? Yes. Similar to how we do the t, right? There's layers here. This is minus 1 squared, which is a plus, second derivative of the Laplace transform of little x. Okay, so that's 3 second derivative of capital X, also known as 3x double prime. That one's actually easier. All right, cool. Now, that's the left-hand side, but we still have the right-hand side. Okay, now we have this layer. All right. So that's the Laplace transform of integral 0 to t of tau sine tau d tau. Now, again, layers here. What are our layers? Well, you can think of it as we have this function, tau sine tau, and then we have this integral. Now, the integral you can think of as an antiderivative. And there's a nice fact that says, oh, if you want to take an antiderivative, then what you do is you divide by s. So this is 1 over s. This is not a convolution. Be careful. Because it feels like convolution, but it's not. So because there's no t minus tau. So if it's antiderivative, 0 to t, then you divide by s, and the Laplace transform of tau sine tau. Sorry, t sine t. Because we're just doing the function on the inside. And now we're in luck. This is on our formula sheet. And what is that? Well, we grab our formula sheet, and it'll be 2. Here, the constant inside is a 1 times t. So it'll be 2 times 1 times s over s squared plus 1 squared. Well, notice the s's cancel. Oops, I forgot to put my square here. S squared plus 1 squared squared. The s's cancel, so we get 2 over s squared plus 1 squared. All right, now we're ready to fill in our boxes because the problem asked us to fill in our boxes. So if we don't do it, we'll lose a point, maybe more, right? Because you have to follow instructions. Instructions, no matter how small, are important. Okay, so we have our x double prime. There's only a single x double prime, so that means that we put 3 into that box. X prime, there's only a single x prime, and that's a negative s squared. X, again, just a single one, a minus 2s. And the last box, right-hand side, is a 2 over s squared plus 1 squared. Done. Done. Wow. All right. Would we like to solve that? No. Do we need to? No. We can stop here. The goal was to transform, and so we did it. Success! Woohoo! All right. On to the next problem. Number 2. Find the following inverse Laplace transforms. Ooh, so now we're going backwards. Okay, so we're starting on part A. We get 2 of them. Find the inverse Laplace of 2s minus 5 over s times s minus 1. All right, well, what do we need here? Partial fractions. So a lot of Laplace transform problems come down to partial fractions problems. So 2s minus 5 over s times s minus 1. Okay, so this is something over s plus something over s minus 1. Clear the denominators. Of course, there are other ways to do this, but this is how I do it. Some people are like, aha, I can just plug in and life is good. And it works if you understand how that works, but I like something I can understand start to finish, and I don't have to think too hard. All right, make good choices. Life is about good choices. So if you plug in, for instance, say s equals 0, that's a good choice. Makes that term go away. You get negative 5 is equal, because that's 0, and that's 0. And over here, you get 0, a times minus 1, it's minus a. So it says, oh, a is 5. All right, another good choice would s equals 1. Okay, plug it in. 2 times 1 minus 5, negative 3. First term goes away, and we get b times 1, which is b. Solve. Well, it doesn't really take a lot to solve that one. B is negative 3. Now, what that means is that this problem can be rewritten as the inverse Laplace of 5 over s minus 3 over s minus 1. Now, we just take them separately. So 5 is a constant, you can pull it out, and the inverse Laplace of 1 over s is 1. So we get 5 minus 3. Then we have the inverse Laplace of 1 over s minus 1, which would be e to the plus t minus t plus t. E to the t. Good, good. And there we go. 5 minus 3 e to the t. Excellent. All right, well, one down. And we had a lot of fun with partial fractions. So let's look at the second one. Okay, inverse Laplace, e to the minus 2s, s plus 1 over s squared plus 6s plus 13. All right, well, let's start. All right, does the denominator factor? Well, we can try for a second. Okay, no, I couldn't do it. I couldn't do it. Maybe it doesn't factor. But perhaps, maybe, just maybe, we can complete the squaring. Okay, so let's think about that. So inverse Laplace, e to the minus 2s, s plus 1. Completing the square, well, we'd have s squared plus 6s. So take the 6, divide by 2, that's 3. Square it would be 9. So I'd need to add 9. So that would make this part a perfect square. But of course I don't have plus 9, I have plus 13. Well, that's okay. I add 4 more, and now I'm the same as I was. And, all right, well, this is inverse Laplace of e to the minus 2s times s plus 1 over, and now we have s plus 3 squared. That's what the perfect square becomes. And I'll denote the other part as 2 squared. All right, good, good. Progress, progress. Now, we're not going to do partial fractions. There's nothing we can do with partial fractions here. It's already been partial fractioned. So what are we going to do? Well, we're going to rewrite it. Now, there's an issue here, which, of course, we should have at least some issue. We're being tested. We notice I have s plus 3 down here, but s plus 1 up there. They're not the same. There's a difference. So we want this to match that. We always want to work with the upstairs part, because the upstairs part, we have an extra feature, which is called we can break addition upstairs. Downstairs, no hope to break addition. That's why we have partial fractions. And so we say, okay, what can I do to the upstairs part to help break it apart? And we say, okay, well, if I want to make an s plus 1 look like an s plus 3, what we can do is we can do the following. Namely, we can write this as s plus 3, right? Now it definitely looks like that, but it's not the same. That's okay. We just say, well, what do we need to do? Well, s plus 3, we should subtract 2. And then we have an s plus 3 squared plus 2 squared. All right. And now remember, we said we had that addition upstairs to work with. Okay, so this is the inverse Laplace of, and I'm going to write this as there's an s plus 3 over s plus 3 squared plus 2 squared minus, now the next term I'm going to be careful of before I get too far, s plus 3 squared plus 2 squared. Now, this looks like cosine, s over s squared plus 2 squared. So I'm good to go. This is number over s squared plus 2 squared. I want the number up here to match this 2. Well, I'm in luck. It is a 2. Now, if it hadn't been a 2, I would put a 2 up here, then I would have compensated in front. And at this point, you're saying, ooh, Steve, you forgot to write something down. Well, I haven't closed it yet. And all of this is times e to the negative 2s. All right. We've now rewritten it, and we have to start thinking about what are our pieces going to be. Okay, so here we go. Piece by piece. What's going to happen? Give ourselves some space here. Well, if we weren't worried about that part for the second, we'll come back and talk about this. This first part is a cosine. So it would be cosine of what? Well, the 2 gives away. It's cosine of 2t. But what about the s plus 3? Now, if there was just s over s squared plus 2 squared, yes, cosine 2t, perfectly right. Spot on. But there's a plus 3 there. Well, that is a shift of sorts. And so that shift coming here corresponds to an exponential on the inverse Laplace. So exponential of e to the minus 3t. Minus 3 because s plus 3 is s minus minus 3. Subtract. All right, now this part, very similar process. If there was just 2 over s squared plus 2 squared, it'd be sine of 2t. But then we have this s plus 3, which means e to the minus 3t. All right, because there's a shift. Shift, exponential function. Cool, 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 cool. Now, if there wasn't an e to the minus 2s, we would be done, life would be good. Now, we have to handle this e to the minus 2s. We saw that a shift inside became an exponential on the other side. What does an exponential on the inside become? Well, it becomes a shift. Okay, so we have to keep track of all these things. There's all these pieces floating around. So there's 2 things that happen. One is we're going to shift by 2 And in particular, that means that t is going to become t minus 2. And we're going to add an on-off switch. So our on-off switch is going to happen at time 2. So we got a u of t minus 2. So when we put this together, so I'll go ahead and put the u at the start. We have u of t minus 2. And we always knew that we were going to have that. As soon as we saw that exponential there, we knew our answer had to have a u of t minus 2. And now we say, okay, we know what our inverse Laplace is without the shift, so it's just the same thing, except everywhere where I see a t, I put a t minus 2. And of course, I'm always paranoid of losing information, so I'm very careful to include parentheses. Parentheses are your friend. They are point-saving devices. And so don't forget them. Don't forget them. And there we go. So we just added the u of t minus 2 at the front, and everywhere where we saw a t, we replaced it with t minus 2, adding the parentheses to make sure we wouldn't lose anything along the way. Good. Nice. Life is good. Are you doing all right? Because we're 2 problems in. We're making great progress. Let's go to the next one. Number 3. Find x of s, which is the Laplace transform of x of t, where x of t is the following. It's piecewise. Aha! That's right. This one comes in pieces. And so, okay, well, that's all right. We can handle that. So what do we need to do? Well, whenever we're dealing with the Laplace transform of a piecewise function, we have to rewrite it in a very particular way. In other words, we need to have on-off switches. Now, the good thing is we know where the ons and offs occur, because we can spot the times that behavior changes, at 4 and at 6. So we're going to have 2 switches. Okay, so here's how we begin. We say, all right, our function x of t, well, is where we're at starting at time 0. So it's this top piece, 14 plus 3t minus t squared. All right, that's the start. Now we hit our first change. So we're changing. So we add u of t minus 4. And what do we put in? Well, this is our on-off switch, so we have to turn something on and have to turn something off. On is going to become what happens afterwards, so we add the after. Off is what came before, so we subtract what came before. And so there we are. All right, and now that's that change. We have a second change, so plus, because we couldn't quite fit it in, u of t minus 6, our second on-off, so we turn on what comes after, which is 0, subtract, turn off what came before, 30 minus 5t, right? Because it's just before 6. No, it's not like, oh, way before 6. No. See, this part was turned off a long time ago. It's this part which is being turned off now. All right, so let's clean that up a little bit. So that's 14 plus 3t minus t squared plus u of t minus 4. And, okay, let's just make this one polynomial. Let's see, there's a minus minus t squared. That makes that a t squared. A minus 5t minus 3t makes that a minus 8t. A 30 subtract 14 makes 16. Okay, plus u of t minus 6. 0, okay, minus 5t makes a 5t. And minus 30 becomes subtract 30. Okay, well, now, here's the thing. We're not quite ready for Laplace transform yet. What we have to do is look at these pieces here. And we have to ask ourselves the question, how can I rewrite this so it's all in terms of t minus 4? Has to be. All right, so we think about t squared minus 8t plus 16. Is there another way to write this in terms of t minus 4? Almost as if they wanted us to be a happy people. it's t minus 4 squared. Oh my gosh. They were nice to us? What? Thank you. How about here? Well, now, here we want it to be in terms of t minus 6, right? So whatever it's attached to, we need to make it look like that. So this was attached to the t minus 4, so it had to look like t minus 4 things. This is attached to t minus 6. And if you look, this is 5 times t minus 6. Again? Wow. So it was all a secret plan the whole time. Okay, cool. So, write it down one last time, and then we'll be ready to go. U of t minus 4 squared, and I'll put it as 5 u of t minus 6, t minus 6. All right, now this isn't u t minus 6 squared, because this t minus 6 is going into the u function. This t minus 6 is outside the u function, so be careful. All right, now we're not done. What we have done, though, is put ourselves in good shape. And in particular, the good shape that we're in is we've written it in the right way. So we can now take the Laplace, just going through piece by piece. So the Laplace of our x of t, which is what we're after. Okay, so 14. Well, 14 is a constant. So we can think of 14 times the Laplace of 1, which is 1 over s. Okay, no problem. And then we have 3, and then we have the Laplace of t squared. Sorry, t. Laplace of t is 1 over s squared. See, I got ahead of myself in my head. Very dangerous thing to do. This, by the way, is a great time to pull out your formula sheet. Laplace of t squared is 2 over s cubed. All right, good. Now, we see this u of t minus 4. So that says that our next piece is going to have an e to the minus 4s. On-off switches become exponential. And what we do is we say, okay, reimagine the piece attached to that u of t minus 4. Replace all the t minus 4's by t. So this really looks like t squared. So that's what we're queuing off of. Say, okay, well, I know how to take the Laplace of t squared. That's 2 over s cubed. And I know that because I just did it over here. All right, then we have plus 5 e to the minus 6s, again, because I see u t minus 6, I am going to have e to the minus 6s. And we look at this part. So, okay, really when we look at this, we should think of this as just the t function. And the Laplace of t is 1 over s squared. All right, and now at this point, we're done. Because it only asked us to find the Laplace transform, and that's exactly what we've done. Wow, I like this one. This is a fun problem. And it's really the key is rewrite, be careful, work it through. Life is good. Life is wonderful. All right, let's keep going. Number 4, a mass spring system with no external forces being set up, which has a mass of 1, a spring with spring constant of 5, a damper with damping constant 2. Initially, the mass is at x of 0 equals 1 with x prime of 0 equals 0. Moreover, at time t equals pi, the mass is hit with a hammer, providing an impulse force of 10. Now, like, word problem. We've got to translate all these words into a differential equation. So, what happens next? This corresponds to, they did it for us? What? Is it our birthday and nobody told us? Okay, all right. Anyways, so we don't have to actually pay attention to the word problem. X double prime plus 2x prime plus 5x equals 10 delta t minus pi. And solve the differential equation for x of t. Well, I will say that there is one teeny tiny bit of the word problem that isn't put into that right there, which is, you see which part? Yes, the initial conditions. We do need that if we're going to solve. Now, technically, we could solve this if we knew how to handle things with delta without Laplace transform. There are ways to do that, but we're not going to go that route. So we're in Laplace transform mindset. We're going Laplace transform all the way. So we begin. So solving a differential equation with the Laplace transform. The key, of course, is we're going to take the Laplace transform of everything. So I'm going to take the Laplace transform of this left-hand side. So 2 Laplace transform x prime, 5 Laplace transform of x is equal to 10 Laplace transform of delta, delta t minus pi. There we go. All right. Now, on a side note, between me and you, don't tell anybody, I graded this problem. And I have a lot of emotions about this problem because I saw lots of things happening here. So I'm going to point out on the way things that happen. And some of them are coming up really quick. Okay, so here we go. How do we take the Laplace transform of x double prime? Well, okay, that's s squared capital X minus s x of 0 minus x prime of 0 from the formula sheet, plus 2 s capital X minus x of 0 plus 5 capital X. Okay, so just taking the Laplace transform of each part is equal to 10, and the Laplace transform of delta will be e to the minus pi s. Good, 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 good. Now, first thing that a lot of people made mistakes on. Do you see these parentheses? People forgot them. I know. We've been saying parentheses are point savers, and we love our points. We love every point. Now, why is that bad? Well, because x of 0 is 1. And so it doesn't go away. You need to multiply it by the 2. So a lot of people miss the fact that it multiplies by 2. Don't forget, parentheses save points. Always, always use, I don't want to say use protection, but it kind of is. Use protection. Put in the parentheses. All right, so let's clean these things up. Of course, x prime 0 is 0. So this part is 1. This part is 1. So what do we have? Well, attached to the x, there's 3 x's. And if we look, what do we have? We have an s squared, a 2s, and a 5. Now, if that sounds familiar, s squared plus 2s plus 5, it should. It looks like these numbers, right? 1, 2, 5, 1, 2, 5. Okay, so there's a minus s. Don't forget there's an s there. And a minus 1. I'll go ahead and put that on the other side. And all right, so that's going to become a plus s. And that's not really a minus 1 right there. It's a 2. So plus 2 plus 10 e to the minus pi s. All right, good. Now, on a side note, another error I saw. And you're probably thinking, Steve, where did this problem hurt you? Right here. It hurt me in the heart because I saw so many good students struggling. Okay, so a lot of people could not read their own handwriting. So they would think like, oh, I have an 2s plus s. So that makes 3s. No. That's a 5. So some people thought their 5s looked like s's. But it also happened the other way. It's that, oh, I have a 2 times 5 or a 25. And so add it to 5. And so another pro tip, read your own handwriting. Which means you've got to write well enough that you can be like, oh, I know what I just wrote down. If you can't read your own handwriting, slow down. Be careful. S's and 5s look a lot alike unless you're very careful. And that's not the only thing that happens. So learn to write legibly. It'll save you. All right. Now, we're almost to the point where we have x. So we divide. And I'm going to separate these two, because whenever I have a little exponential part, I like to have that separated out. So I'm going to have an s plus 2 over s squared plus 2s plus 5. And then I'm going to have a 10 over s squared plus 2s plus 5. All right. So we are getting close. We're rounding the corner. And now to the number one error that happened on this test. Completing the square. And I know you're like, completing the square? That's something we learned a long time ago. I know! So that's why it hurt in the heart. All right, so how do you complete the square? S squared plus 2s plus 5. What comes next? Well, take the middle term, divide by 2. 2 over 2 is 1. 1 squared is 1. So that's the part that's squared, but I need to get up to a plus 5, so I add 4. Which means that our denominator is really s plus 1 squared plus 2 squared. So many people put s plus 2 squared plus 1 squared. Well, the problem is it doesn't work. If you have s plus 2 squared, that would be s squared plus 4s plus 5. Be careful. Be careful. It doesn't hurt to double check, you know. Expand out and just make sure it gets you back to where you started. And if it doesn't, whoops, mistakes were made. And so that's fine. It's not terrible to make mistakes as long as you catch them. It's like it was never made. That's my secret. I make mistakes, but I tend to catch them. Not all the time, but frequently. And so, all right. So back to our problem. Now that I've worked through, I've had my my therapy session, I can finish the problem. All right. So we're going to replace the denominators by s plus 1 squared plus 2 squared. So that would say downstairs would be an s plus 1 squared plus 2 squared. And again, we're going to have an s plus 1 squared plus 2 squared. Let's work in the upstairs. Now, for the first one, I have an s. And this is kind of a callback to problem 2. It says, what do we want to do? Well, we'd like to make it look like s plus 1. So we say no problem. We'll just put it as s plus 1 plus 1. And upstairs, okay, let's come to this one. I have 10. Well, that's okay. We have a number. And that says we're thinking sign. Well, I see a 2. I'd like a 2 upstairs. So I'm going to make it a 2. Of course, I'll add a 5 in front, because then that sets us up as a sign. Now, if you're paying attention, you're probably like, wait a second, Steve. Take your first term, split it in 2. Don't we also, in the second term, which we should have a 1, but shouldn't we want to have a 2 like we do there? And you're right, we do want to have a 2 there. So what should we do? We'll put a 2 there. But if I put a 2 here, how do I get to 1? Multiply by half. Right? Half times 2 is 1. So I've broken it up, and I'm setting myself up for success. You know, it's good to set yourself up for success. It's better than the option, which is to set yourself up for failure, which we don't want to do. We're not those people. All right, here we go. Now, this is the bulk of the work. And indeed, even if you got just to here, I'll be honest, that was more than half the points. And then it was very strict from there on as far as grading goes. All right, so how do we finish? Well, we just think about what happens with each piece. Now here, this is a cosine piece. Think of it as s over s squared plus 2 squared. So that would normally be a cosine of 2t, which is great, except that s plus 1, a shift here becomes an exponential on the other side. So we have e minus t. Then the half, and here a similar thing. 2 over s squared plus 2 squared would be a sine of 2t, but we have that shift by 1, so that becomes an exponential, e to the minus t. Plus, then we have the 5. Now, this is where we have to be careful. Just this piece here. That by itself, we know what it looks like. Sine of 2t e to the minus t. So this looks like sine of 2t e to the minus t. But there's an e to the minus pi s. That's exponential. Exponential going to become shift. So we have an on-off switch, u of t minus pi. And then we're going to take our expression, and everywhere where we see a t, it's going to become a t minus pi. So that's sine of 2, t minus pi, e to the minus t minus pi. Got to get all the t's, both of them, and update them. Now that's the answer. We'll just rewrite it a little bit more cleanly. So we have cosine, so this is x of t. That's cosine 2t e to the minus t plus 1/2 sine 2t e to the minus t plus 5 u of t minus pi sine 2 times t minus pi e to the minus t minus pi. A lot to write down, but that's just because cosine and sine take up space. Now there is one thing you can do if you are so inclined, which is to say that this part right here, this is the same as sine of 2t. You don't need to make that change. And the reason it's the same is if you multiply the 2 through, you get 2t minus 2 pi. Well, sine is 2 pi periodic, so adding or subtracting the 2 pi doesn't affect the outcome. You can't do that here because the exponential is not a periodic function. And there we go. Our answer. Our lovely, lovely answer. Lots of places for small mistakes. So I know a lot of students struggled, but that's why we practice, so we don't do it again. You know, you may have said, look, I may have made a mistake this time, but you won't catch me next time. Good. I don't want to. I want you to succeed. And I hope that we do succeed. All right. Well, on to our next problem. Number 5. We're given y double prime minus 4y prime plus 2y is x plus 3, and that y, which is our sum, 0 to infinity cn x to n, which we can write in the following way. Then write expressions for c2 and c3 in terms of c0 and c1. So c0 and c1, those you can think of as initial conditions. Oftentimes, we like to think of c0 and c1 as this is c0 is y of 0, and c1 is y prime of 0. So it says, okay, I'm not going to tell you the initial conditions, but once you know the initial conditions, that tells you what everything else is. All right, so how do we do it? Well, the nice thing is we don't have to find the recurrence relationship. So we're going to say, look, I'm just going to do just enough, which is a great way to do a problem, right? I'm going to get the points, but I'm just going to get it in an efficient way. So we start by saying what? Well, we say y is, we're just going to copy what we have here. We're going to go up through the c3 term. Why? Well, because we want to get something at c3. We don't care about c4 and higher. So y is c0 plus c1x, c2x squared, c3x cubed, dot, dot, dot. Well, we need y prime. So that's c1, 2c2x, 3c3x squared, and we need y double prime. 2c2, 6c3x. All right, now I'm going to make a small digression here. When we're after c2 and c3, Where are we going to get that from? Well, we have our initial conditions giving us C0 and C1, and that's because it's second order, so two initial conditions. So it turns out that C2, we need the constant term. That will give us C2. C3, we're going to need the x term. In other words, when I talk about the constant and the x, I'm looking for these coefficients. So here we go. X plus 3 is equal to y double prime 2c2 plus 6c3x plus dot 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 minus 4y prime c1 plus 2c2x plus dot dot dot, because I only need the constant, the x term, so I don't even need this x squared term, and plus 2 times y, c0 plus c1x plus dot dot dot. So we now group. These are 2c2 minus 4c1 plus 2c0. That's my, I grabbed all the constants. Remember that these multiply through. Plus, now, the coefficients for x, 6c3 minus 8c2 plus 2c1 x, and of course everything else. So at this point we say, aha, matching, matching. Well, what does that mean? Well, it means that the 3 has to match with the coefficient. That's a constant term. And secretly there's a 1 in front of the x, and that has to match what's in front of the x. All right, so let's start with the constant term. So we know that 3 is equal to 2c2 minus 4c1 plus 2c0. We need to solve for c2 in terms of c0 and c1. How do we know that? Because that's what it says, c2 in terms of c0 and c1. So we can move things across. We'll get 2c2 is equal to 3 minus 2c0 plus 4c1, or we get c2 is 3 over 2 minus c0 plus 2c1. All right, good. Progress. Good progress, too. Good progress. Okay, now, the next part, the coefficient for x. We'll get that 1 is equal to 6c3 minus 8c2 plus 2c1. Okay, do something similar. Move the parts across. So 6c3 is equal to 1 minus 2c1 plus 8c2. Now, small catch. See, previously it was c0 and c1 already. Life was good. Here we have c3 in terms of c1, c2. We want c3 in terms of c0, c1. So that says we have to do something about that c2. So what can we do? Well, the good news is we know something about c2. We can use the piece of information above. So this is 1 minus 2c1 plus 8 times 3 halves minus c0 plus 2c1. So if we work this out, we get 1 minus 2c1. 8 times 3 halves. Well, 8 divided by 2 is 4. 4 times 3 is 12. Minus 8c0 plus 16c1. So 1 plus 12 makes 13. Then we have a minus 8c0. And then minus 2c1 plus 16c1 makes a 14c1. Now, is this the answer? Almost. That's 6 times c3. And so dividing gives us c3 is 13 over 6 And then we have 8 over 6, but that can simplify to 4 over 3, and then 14 over 6, which again we can simplify to 7 over 3. So 13 over 6 minus 4 over 3 C0 and 7 over 3 C1. And there we go, C2 and C3 written in terms of C0 and C1. All right, good. All right, well that's 5 down, 1 to go. Let's go and finish the test. Number 6. We're given that y is the sum from 0 to infinity of Cn x to the n is a solution to the following differential equation. So we have our x squared minus 4y double prime minus 2y equals 0. Y of 0 is 4. Y prime of 0 is negative 3. Okay, so that's what we're given. And then we need to find a recurrence relationship, and they made it bold, meaning we can't avoid it. We must find a recurrence relationship. And then we have to find the values for C0, C1, C2, C3. Now there's some good news. C0, C1, C2, C3, we can find C0, C1 pretty quickly. C0 and C1 are initial values. So C0, this is y of 0, and that's 4. And C1, that's our y prime of 0, and so that's negative 3. So we're already halfway through the second part. Even just this, that's worth like a point, right? That's not so bad. We can get some points. Okay, so here we go. We know what y is. We'll just copy it again for reference. 0 to infinity, Cn x to the n. We can take a derivative, so that's the sum. 0 to infinity of n c sub n x to the n minus 1, right? Bring the n down, subtract 1. And y double prime is the sum 0 to infinity n times n minus 1 c sub n x to the n minus 2. And we went to y double prime because we needed a y double prime. Okay, good. Now we're going to go through and use this to rewrite our differential equation. So we have x squared minus 4, y double prime minus 2y, of course this equals 0, is equal to, well, x squared, well, okay, I'm going to write it as x squared y double prime minus 4y double prime minus 2y. I do want to separate that. And I was debating now or later. Well, let's do it now. Okay, so this is x squared sum n equals 0 to infinity n times n minus 1 cn x to the n minus 2 minus 4 sum n equals 0 to infinity of n times n minus 1 c sub n x to the n minus 2. So I'm just copying y double prime, and minus 2 sum n equals 0 to infinity of cn x to the n. All right, good. Now, good news, a lot of these are in good shape. So what do I mean? Well, notice the x squared here, I can bring it in. And that x squared with x to the n minus 2 makes x to the n. Life is good. I have x to the n here. Life is good. Automatically. Nice. Now here, I don't have that. So I'm going to do a shift. So what we'll do is we'll say, let's let k equal n minus 2. Now, while we do this, normally we say, oh, that would mean that if we start here at 0, that would say we start at negative 2. Well, actually, we have some choices here. Because when we plug in 0, we get 0. When we plug in 1, we get 0. So we could, and we will, change it so it starts at 2. Now, in the meantime, we don't need to change anything about these sums, but we will just change our index. So n is acting like a dummy variable. In other words, we can change the symbol to anything we want. So we'll make them all k, just so it's easier to see what's going on. So we have the sum, k equals 0 to infinity, and this will become k times k minus 1, c sub k x to the k. We multiplied the x squared through, life is good. Minus 4, sum, when n equals 2, k equals 0, so k equals 0 to infinity. Now, if k is n minus 2, n is k plus 2. So the n becomes k plus 2. The n minus 1, k plus 1. The c sub n, c sub k plus 2. And then x to the k. Minus 2, sum, k equals 0 to infinity, of c sub k x to the k. Good. And we're in our happy place because our powers are all the same, xk, 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 which is the reason we want to do this. We're going to push everything into a single sum, and we want our powers to be consistent because not only are we pushing into a single sum, we're going to pull out and have just the x to the k on the end. So the x to the k, good to go. We also, our stars are the same. Bonus. So we don't have to pull off any terms at the beginning. So when we put all of this together, it gives us the following. We have the sum from k equals 0 to infinity of, here we have k times k minus 1 c sub k minus 4 k plus 2 k plus 1 c sub k plus 2, and then here minus 2 c sub k, and all of that times x to the k. So we're just grabbing our coefficients, and don't forget to do your multiplications. Now you can do some things to this expression. One thing we could do is if you see, it's like, oh, we have two terms involve c to the k, and so this is k squared minus k. Here it's minus 2, so you can make this the following. You can say, aha, this is really the same as k squared minus k minus 2 c sub k, and minus 4 times k plus 2, k plus 1, c sub k plus 2. That's just another way to write that expression. But whether you keep it here or keep it there, this part is the key. Now, I boxed it, but I forgot to add one thing. So, very silly me. What did I forget to add? This is the coefficient for x to the k on the right-hand side, which has to match the coefficient for x to k on the left-hand side, which is 0. So all this equals 0. There we go. See? I left space. No, I didn't. Grrr. I will note that, and this is, we'll even add a little comment here for k greater than or equal to 0. Okay, so all that equals 0. Now, you can maybe get lucky. Let's see if we can get lucky here. The k squared minus k minus 2, does it factor? I think it does. And let's see, it would be, I need two things that multiply to negative 2 but add to negative 1. So I think k minus 2, k plus 1 would do that. Let's check. K squared plus k minus 2k is minus k minus 2. Yeah, it does that. Notice how both terms have a k plus 1, although this other k plus 1 is very poorly written. And even after I just finished talking about make-legible handwriting on a previous problem. So you could, for example, divide out by k plus 1 and get the following. K minus 2 c sub k, then minus 4 k plus 2 c sub k plus 2 is equal to 0. So that's another way you could do it. Okay, all right. So anyways, either way, full points, you've got your recurrence relationship. Now, we need to get C2 and C3. So how do we do that? Well, for that, we use our recurrence relationship. And we can use either version. And, okay, well, we'll use this one. Why not? Because this is probably the one that most people would stop at. It's not so clear that you can clean it up even further. So, let's suppose we're after C2. So we're going to do it by starting with k equals 1. K equals 0. You always start where your recurrence starts. So plug in k equals 0. We get 0, 0, minus 2. So minus 2 times C0. And then here we get 0 plus 2, 0 plus 1. So that's 2, 1, and 4. So that's minus 8 C2 equals 0. Well, you can move it across, and that says 8C2 is minus 2C0, but C0, we know, is 4. Okay, so we get 8C2 is negative 8, or that tells us C2 is negative 1. All right, that's nice. How about k equals 1? Okay, 1 minus 1 minus 2. Oh, we got lucky again. So it's another minus 2. C1. And here we have 4. 1 plus 2 is 3. 1 plus 1 is 2. So 4 times 3 times 2, that's 24. Okay, so minus 24. And then 1 plus 2 is C3. All right, so again, 24 C3 is minus 2 C1. But do we know C1? Yes, it's negative 3. Okay, so minus 2 times minus 3 is 6. I say, okay, great. Well, that tells us that C3 is 6 over 24, which is 1 over 4. All right, so for the coefficients, C0 is 4. C1 is negative 3. Those are our initial conditions. C2 is negative 1. And C3 is 1 over 4. And that's from our recurrence. And that's as far as we needed to go. And there we go. Recurrence relationship, coefficients. Life is good. Our test is over. Whew, good. And if we've done well on the semester, then actually maybe we're just done. And that's the goal. All right. Well, thank you. Thanks for joining me. I hope you did well. And if you didn't, I hope you picked up some things that will help you do better, and so that you can do great on your next exam. All right. Have a good day. Bye.